In this video, we are going to be talking about the energy stored in an atom according to the Bohr model. Okay, so basically, there is an energy that is being stored in an atom, of which it is from this energy that an atom experiences an electrostatic force, which is converted into a centripetal force. Okay, like we talked about in our previous video. Now, in our previous video, we talked about the equations and the usefulness of these equations in calculating the Bohr's radius and then the velocity of an electron, okay, that is moving in an atom. While on this video, we're going to talk about the energy stored. So if you need more insights on the radius and velocity, you might want to watch those videos still on our playlist, okay? And then you can then come back to watch the energy stored in an atom. Okay, now basically we talked about two postulates, okay, that we used in deriving those equations. We first said that the centripetal force is equal to the electrostatic force, which is mv squared divided by rn is equal to kze squared divided by rn squared. Okay, now this was one of it. Okay, let's call this equation 1. And then we also say the angular momentum, which is mvr, is equal to n times Planck constant divided by 2 pi. Okay, these are the two useful equations we started with that we used in deriving those other equations. Okay, now next thing we're going to do is we're going to derive an equation for the energy. Now it is important to take note that the net energy is simply the sum of the potential and the kinetic energy. So we're going to say the energy for an orbit n is equal to the kinetic energy plus the potential energy. So if we can find a value or a formula for solving the kinetic energy and then for potential energy, when we sum them, what we get is the net energy for a particular orbit n in the atom. Okay, now how do we solve for the kinetic energy? Now generally we're going to note, or rather we will call that kinetic energy is 1 over 2 mv squared. Okay, 1 over 2 mv squared. 1 over 2 is the number constant, m is the mass of an electron, and v is the velocity is used in moving around the orbit. Now we can choose to substitute v squared from this equation, right? So from equation 1, we're going to say from equation 1, so from equation 1, notice that r cancels r at the bottom. So if we make v squared the v squared the subject of the formula, we're going to get v squared is equal to k times ze squared divided by m r n. Okay, here's what we're going to get. We're going to get v squared equals kze squared divided by m r n. Okay, now let's substitute this v squared into this formula. Hence, we're going to get kinetic energy. Okay, kinetic energy would then be equal to 1 over 2 times m, and then v squared is kze squared divided by m r n. Now m cancels m, so we're left with kinetic energy is equal to kze squared divided by 2rn. Now also recall that k here is Coulomb's number. Okay, now k is Coulomb's number, and it has a value or a formula for solving it. Now we know that k is equal to 1 over 4 pi a naught, right? So if we make use of some substitution into this equation, we're going to get kinetic energy would then be equal to z times e squared divided by 2 multiplies 4 pi e naught, right? So we get 8 pi e naught times rm. I'll call this equation 3. Now here is the formula for calculating the kinetic energy. Now we just succeeded in deriving the formula for calculating kinetic energy. Next thing we want to do is get that of potential energy and then substitute into this equation. Okay, now if you recall, so I'm going to talk about potential energy over here. Now if you recall, we do know that in electrostatics, electric potential is equal to the work done per unit charge in an atom. Okay, that is the work done in bringing a unit charge from infinity to a point in an electric field. That is why we're having the negative sign there. Where W here is the energy, okay, is the work done, and this W here is also called electric potential energy. So we can represent or replace W with potential energy in the sense that we're going to get V is equal to minus PE divided by Q. Now let's make PE the subject. Okay, if we should make PE the subject, we're going to get potential energy will then be equal to minus V times Q. Now, how then do we break this down to get a simpler formula which we can then substitute into the general form? How then are we going to do that? Okay, now you notice that V is also equal to, okay, but V is E times R, right? I'm going to write Rn, okay? Electric potential is equal to E times R, or Rn rather. And electric field intensity on the other hand, okay, we're going to get V is equal to electric field intensity on the other hand is force over charge. So we have force over charge times Rn, okay? We have V is equal to force is kZe squared divided by Rn squared times the Q at the bottom. So we have Q times Rn. Now Rn cancels R. So we're left with V is equal to K times what else? Now you notice that E and Q, they are similar, okay? The only difference is that E is peculiar to an electron and Q is peculiar to any charge, okay? So if Q is an electron, Q can cancel out one E. Then we'll be left with Kz times E divided by Rn. Here's what we're going to get. So substitute for V into this formula, we're going to get potential energy is equal to minus kZe, and then again Q over here is also what now? E. So I'm going to multiply by E. Okay, so anyway you see Q represented as E to tell you that we're dealing with an electron, divided by, over here we're having Rn. Okay, is it similar to what we're having here? Okay, almost there, but we still have to do one or two maths. Now you recall again that K is 1 over 4 pi E naught. So you substitute for K as 1 over 4 pi E naught. We're going to get potential energy is then equal to minus Z E times E, that gives you E squared, divided by 4 pi epsilon naught Rn. Now this is our formula for calculating the potential energy. Next thing, we're going to complete it by solving the total energy in the system. So the total energy in the system, which is E with the subscript of n, okay, is equal to the kinetic energy is Z times E squared divided by 8 pi epsilon naught Rn, okay, plus, so we're having a negative sign here, so the negative sign will still remain there, okay, so we're going to have minus instead, Ze squared divided by 4 pi epsilon naught Rn. From here, we're going to do the math. Now, the LCM here should be 8 pi epsilon naught Rn, okay. When this comes in here, we're going to have Ze squared minus, this comes here, that's 2, so we have minus 2Ze squared, that gives me minus Ze squared divided by 8 pi epsilon naught Rn, okay. So it therefore means that the energy at any level n is equal to minus Ze squared divided by 8 pi epsilon naught Rn, okay. That's what we're going to get. Yeah, that's what we're going to get. Now from here, what we want to do is make substitutions into this formula to see if we can get something simpler, okay. That's what we want to do. So we're going to make substitutions into this formula. Okay, now Rn, from our other video we derived the expression for Rn, and we did say that Rn is equal to the Bohr's radius, okay, times n squared divided by Z. Okay, that was all said. And we know that Bohr's radius has a value of around 5.29 times 10 to the power of minus 11. If we substitute that in, we're going to have En equals minus Ze squared divided by 8 pi epsilon naught, okay, AB is around 5.29 times 10 to the power of minus 11 times n squared over z, okay. You notice that this one can go to the top, the z can go to the top, multiplying this one, so we're going to get minus z squared e squared divided by 8 pi epsilon naught n squared times 5.29 times 10 to the power of minus 11. Now we're going to be substituting in the values, okay, for e, for epsilon, okay, into this expression, and so we're going to get, okay, by using our calculator. So we're going to get a value of minus 2.181 times 10 to the power of minus 18, okay, z squared, okay, divided by n squared, okay. Now this our answer energy is in joules. We can as well convert to electron volts. Please take note that 1 electron volt equals the charge of an electron, which is 1.602 times 10 to the power of minus 19. So you can then convert. If 1 electron volt is this in joules, so this value in joules will be how many electron volts. It means we have to divide this value by the charge of an electron. So dividing, we're going to get a value of En is going to equal minus 13.61 z squared divided by n. Now this our answer is in electron volts. Now here is how you solve for the energy, okay, of the electrons, hydrogen atom, or in atoms in general, okay. So here is the procedure, or here are the procedures rather. This is simply the formula that we need to know in the end, okay. Now this one looks quite easy, okay. For an energy level, this should be n squared, okay. For an energy level 1, n should be equal to 1, and then z remains the atomic number of, or the number of photons of that particular atom, okay. So that is how it is being done. So for hydrogen, to be specific, z is always equal to 1 because we always have 1 photon, okay, or for ions in general. But for atoms that are not hydrogen, like the lithium, beryllium, they become 2, 3, and so on and so forth. Now it's always important, or rather also important, to talk about the energy differences. Now we talked about electrons that are in unstable orbits. We said that when an electron is in an unstable orbit, what happens is that it drops to a stable one. Now as it do this, it gives out energy in form of what now? Light, okay. Now that light that it gives out, it usually has a frequency, okay. It gives out light waves in form of light, and it has a frequency which can also be calculated using the Rydberg's formula. We're also going to talk about that right now. So talk about the Rydberg's formula, okay. So the energy is given as HF, okay. You should be familiar with this formula by now. And then it is also equal to the change in the energy, that is the initial energy minus the final energy. Now what is the initial energy? Let's say these are the two states. This is the higher energy level and this is the lower energy level. Now it is having an initial energy here. When it drops to this stable state, it's going to be having a final energy. Now the change in this energy level is what will give us the energy of the radiation that is being given out or released, and that is the change we are having here. Now we already stopped at this formula, okay, but we're going to be using this one instead, that is in joules, simply because the formulas that we're going to incorporate into it, which is H, okay, is going to be in joules second. So it is important that we make use of joules as well. So we're going to make use of this formula that we're having here, okay. We're going to make use of that one. So we substitute into what we're having here. We're going to have HF is equal to, for the initial energy, we're going to write Ni, okay. That's what we're going to do. So we're going to have this one as a constant, so we know it's going to come out. So we'll have minus 2.18 times 10 to the power of
minus 18, okay, times, okay, in brackets, we're going to have z squared divided by ni squared for the initial. Okay, that's what we're having here. The reason I'm putting this one in brackets because I don't want to write it twice. It's like wasting space and time. Okay, so we're supposed to have minus, right? But then, yeah, we're going to have minus because we're having a negative number outside. So when we open this bracket, we're going to get the whole thing. If this one to open the bracket, it should be giving you plus. But since we're factorizing, it will remain minus. So we're going to get z squared divided by nf squared. Okay, this is what we're going to get. So from here, doing the maths, we're going to have f is equal to, or rather, let's just say hf is equal to, bringing out z squared minus 2.18 times 10 to the power of minus 18 times z squared in brackets 1 over n I squared minus 1 over n f squared. Okay, now you also realize that we can get rid of this negative sign by just interchanging these two. Okay, by just writing f here and I here, we can interchange this because it's like having 1 minus 2. When you do 1 minus 2, you get a negative number. That negative number cancels out this. So if I interchange here, this negative sign will go, and that is what we're going to do. So I'm going to replace this one as f, and then replace this one as I. Now immediately I do that, this negative sign is going to disappear. Okay, take notes. It's a simple math. Now after doing that, we want to solve for the wavelength of the light, or the frequency. Okay, this is the frequency. We can just divide by h to get the frequency. Then to get the wavelength, we recall that c is equal to f times lambda, okay, of which c is the speed of light. So from here, we're going to substitute for f. Now f will then be equal to c divided by lambda. If we substitute into this formula, we get h times c divided by lambda is equal to 2.18 times 10 to the power of minus 18 times z squared, okay, divided by 1 over n squared f minus 1 over ni squared. Okay, here's what we're going to get. So from here, let's make 1 over lambda the subject. Now we're making 1 over lambda the subject because it is something that has a peculiar property, and this is known as the wave number. Okay, so we're going to divide both sides by hc, so we get 2.18 times 10 to the power of minus 18, okay, times z squared divided by hc in brackets 1 over n squared f minus 1 over n squared I. Okay, now we'll do the maths. We'll do the maths for this. On our calculator, we're going to get 2.18 times 10 to the power of minus 18. Okay, now z will be equal to 1 because this formula is what we use in calculating the wave number for the energy that is being given out in an hydrogen atom or in a hydrogen atom. Okay, so it is peculiar to a hydrogen atom. Now h is 6.62 times 10 to the power of minus 31, and the speed of light is 3 times 10 to the power of 8. Now we are getting a value, and that value is 1 divided by lambda, okay, and then it is equal to this value, which I'm going to call the Rydberg's number. This is how it is represented, okay, in brackets 1 over nf squared minus 1 over ni squared, okay, where rh is equal to 10976837 per meter. Okay, that's the unit for measuring the Rydberg's number. Okay, the Rydberg's number can be found in most scientific calculators, so you don't really need to cram it. And this is to 7 decimal place, if I'm not mistaken. That's 1 2 3 4 5 6 7. So approximately 1.097 times 10 to the power of 7, okay, per meters. That's the unit. Now everything you're having here, 1 over lambda, is usually referred to as the wave number. Okay, it is v with a dash on top, that is bar v, is called the wave number. So this is how you calculate the wavelength of the radiation that is being given out as the electron moves between two different energy levels. So we have the final level 1 over the final level squared minus 1 over the initial level squared. Okay, now this is how the energy for Bohr's model is being done or dealt with. If you have a question, don't forget to put it in the comment section. And if you did learn something new, most likely you will. Okay, from this video, don't forget to smash the like button and then click on the notification bell, of which you can't do that except you subscribe. So don't forget to subscribe to the YouTube channel to help us create more videos for you, and then you'll be one of the first few persons that will get notified when a new video is being created. See you in the next video. Bye.